In this lesson, we will be studying absolute value functions. Check out this function. F of x is equal to the absolute value of x, which is equal to x as long as x is positive, or it's equal to the opposite of x if x happens to be negative. Okay? Now, geometrically speaking, the absolute value of a real number is its distance from zero, right, on the number line. So as a result, the absolute value of a real number is never negative. The absolute value of a real number is always positive because it's defined to be distance. So the absolute value of a number is always greater than or equal to zero. Now, based off of the definition of an absolute value, right, of absolute value of a number, we can now consider the definition of a function that is the absolute value of another function. Let me write it down so that you can understand. So here we have the absolute value of a function. The absolute value of a function f of x is equal to f of x as long as f of x is positive. But the absolute value of f of x is equal to the opposite of f of x as long as f of x is negative. So to graph a function of this form here, we have to leave the graph of f of x unchanged. Leave it alone. Leave it the same as long as that portion is on or above the x-axis. Because think about the Cartesian plane, anything that's on the x-axis or above it is positive. So leave the function unchanged for any portion of the graph that is on the x-axis or above it. But any portion that is below the x-axis is negative, right? So you're going to have to get that portion of the graph and reflect it across the x-axis. Okay? So let me show you an example of us doing that now. All right, check out our first example. Let f of x equal this quadratic function x minus 4 quantity squared minus 3. Then I want you to graph both this function f of x and the absolute value of that function. When we're done, we're going to find each of their domains and ranges. Now, let's first graph this function here. This is a quadratic function. And we know that the graph of any quadratic function is a parabola. So this is going to be a parabola. Now this parabola will be shifted 4 units to the right and then 3 units down. So let's go ahead and graph this function now. So here's the graph of f. This parabola, again, was shifted, right, from the origin. The origin is the vertex of the parent function, the most basic quadratic function. And that vertex got shifted 4 units to the right and then 3 units down. So here's the vertex for -3. And you also have some additional points here that I've called out for you just in case it's helpful. 5, -2, and 3, -2 are also on the graph of this parabola. Of course, there's infinitely many points, but I just wanted to call out a few of those points. This is the graph of f of x. Now, what we need to do is graph y equal to absolute value of f of x. Now, according to our definition that we were speaking to a minute ago, what we need to do is the portion of this graph that is above the x-axis, on or above the x-axis, which are these pieces here. I'm going to highlight them really quickly. This portion and this portion, leave those portions unchanged because those portions are already positive. They have positive function values or positive y values, positive output values. However, the portion of the graph that is below the x-axis, this whole portion of the parabola has negative y values or negative function values. So we're going to have to reflect this portion across the x-axis in order to find the absolute value of these function values, okay? So we're going to reflect this entire portion across the x-axis. That means, for example, this point here, 3, -2, will become 3, +2. This point here, 4, -3, will become 4, +3. 5, -2, for example, will become 5, positive 2. So I'm going to take this whole piece here, reflect it across the x-axis, while leaving these portions that I've highlighted, leave those unchanged. So then this is what the graph is going to end up looking like. Notice that this whole portion here got reflected across the x-axis. Okay, this is the graph of the absolute value of f. And notice that the vertex of this parabola here, 4, -3, ended up jumping up to 4, 3. I couldn't really fit these ordered pairs as far as labeling them, but this is 3, +2, and this is 5, +2. Okay, so again, I just took the portion that is below the x-axis, reflected it across the x-axis in order to get the graph of y equal to f of x, y equal to the absolute value of f of x. The last thing we need to do is write the domain and the range for each of these functions. So let's do that now. Now, the domain for both functions is all real numbers. Now, we know this because you can look at the graph and you can hopefully see that both graphs extend indefinitely in both directions. So they go forever to the left, forever to the right, right? These graphs are getting wider and wider and wider. So is this one, going forever to the left and forever to the right. Just as a reminder, the domain by definition is a set of all of your x values. You can go ahead and plug in any real numbered value into either one of these functions and get a real numbered output. So the domain is all real numbers for both. But what is different is the range. The range for f of x goes from -3, right? That's your minimum, and it goes in infinitely high. But the range for the absolute value of f of x, I mean, the lowest it goes is the x-axis. So that's going to be 0 all the way up to infinity. Check out this example. Use this figure to sketch the graph of y equal to the absolute value of f of x. So what I have shown here is a graph of f. So let me put f nearby. There. This is the graph of f. What we want to show is the graph of the absolute value of this function, right? We want to show this graph of the absolute value of f. So what we're going to have to do is take the portion of this graph that is below the x-axis and reflect it across the x-axis, right? So notice that this function f has 3 different pieces. This is going to be an example of a piecewise function. This piece is a constant function, right? It's a horizontal line. So this is a constant. This is constant. And then this piece is a piece of a parabola. And then over here is a diagonal line. So this is a linear piece, right? Linear function. So you got a constant, quadratic, and then linear, right? And so there's 3 different pieces. The linear piece we can leave unchanged because this whole linear piece is on or above the x-axis. So we're good. It's the quadratic and the constant pieces that we need to reflect across the x-axis. So basically the horizontal line and the piece of the parabolic curve that we need to reflect across the x-axis. When we're done with all of this, we want to state the domain and the range for each of these functions as well, okay? But we'll do that at the end. So this is what we have. Notice that the linear piece stayed the same, right? It's still going through 6, 3. It's even going through 3, 0, right? Nothing changed there. But this parabolic piece and this constant piece, oh, by the way, I accidentally, if you want to rewind this video, I mislabeled this ordered pair. I accidentally had it as -2, 0 instead of 0, -2. Quite embarrassing. So anyway, make sure this is labeled as 0, -2, not -2, 0. But anyway, so these 2 pieces got reflected across the x-axis, all right? So this would be the sketch of the graph for the absolute value of f. Now, let us write the domain and range for each of these functions. Now, the domain for both functions is all real numbers because the graph goes forever to the left and forever to the right. Same thing is true for the absolute value of f of x, right? Forever to the left, forever to the right. So all real numbers there. The range for f, you go from the minimum, and the minimum happens to be -3. And so you go from the minimum to the maximum. There is no maximum because it goes infinitely high. So the range for f of x is -3 to positive infinity. However, for the absolute value of f of x, the minimum here is 0. 0 all the way up to positive infinity. So from 0, write it down here, all the way to positive infinity. Check out this next example. Graph each of these equations, okay? The first one is y equal to 2x minus 1. Now, I hope this looks very similar, not similar, excuse me, familiar to you. This is an equation written in slope-intercept form, which is y equals mx plus b form. The slope is 2, and the y-intercept is -1. So here is the graph of that line. Again, the y-intercept is -1. That's where I started. The slope is +2. Remember that you can write the slope as rise over run if you'd like, as a ratio, because that's what it is. So if you'd like, you can write the slope, instead of just writing it as 2, you can write it as 2 over 1. So just to reiterate that it's up 2 units and then to the right by 1. So up 2 units to the right by 1 leads me to the point 1, 1. Up 2 units again and to the right by 1 leads me to the point 2, 3. If you went down 2 units and to the left by 1, that's also positive 2 slope. It would lead you to -1, -3. So these are just a few of the points that are on the graph of y equal to 2x minus 1. Okay? So I hope that's a good little review of graphing a line that's in slope-intercept form. What we want to do now is graph the absolute value of 2x minus 1. Just like before, we want to take the entire portion of this line that is below the x-axis, which is this piece here, and we want to reflect it across the x-axis. So this is going to turn out to be a V-shaped graph because this portion will remain the same, and then right here at this x-intercept, which we didn't find the x-intercept, but there is an x-intercept here, at this point it jumps back up above the x-axis. So it's going to be like a V-shaped graph. Let's show that now. So here it is, folks. And again, it turned into a V-shaped. Instead of a line, it's a V-shape. I want you to notice some things. I want you to notice that the x-intercept, excuse me, it's singular, the x-intercept is the same. So the x-intercept does not change, okay? But what does change is the whole portion below the x-axis goes above the x-axis, and instead of a line, you get a V-shaped graph. Okay, let us write down the domain and range for each of these functions. Okay, I hope you can see, or I hope you can agree with me, rather, that the domain for both of these functions is all real numbers. We already know that the domain for any linear function is going to be all real numbers because lines, by definition, go indefinitely in both directions, right? So it's going forever to the left, forever to the right. And the same thing is true for this V-shaped graph. It's going forever to the left and forever to the right, okay? As far as the range here for this function is going infinitely low, infinitely high. So the range is all real numbers. If I can squeeze that in there. Okay. There is no minimum. There is no maximum, right? It goes infinitely low, infinitely high. However, over here, the minimum, there is a minimum, and it's 0, right? That's the lowest y value, and it goes infinitely high. So for the absolute value of 2x minus 1, we have the range of 0 all the way to infinity, okay? That's a little sloppy, but that says 0, comma, and then the positive infinity symbol. This next example is going to be really cool, I think. So we're going to solve this absolute value equation. The absolute value of 2x plus 1 is equal to 7. Now, I'm going to show you a graphical approach first. After all, our course is PreCalculus, but it's a graphical approach to PreCalculus. So, I mean, that's the name of our textbook as well. So I feel obligated to show you a graphical approach for solving this equation, but not just obligated, like I really want to show you because I think it's better for your learning. A lot of students are visual learners, and so if I can show those students a picture of what we're doing, it helps them get a deeper understanding of the mathematics. So please bear with me as I endeavor to show a picture, a graphical representation of the solution of such a absolute value equation. When I'm done with showing you the graphical approach, I think I may show you an analytical approach that will most likely be a shorter process. The analytical approach may be a shorter process. Some of you may prefer the analytical approach just because it's shorter, while others are going to benefit and may prefer the graphical approach just because it gives you something to look at, right? Or some of you may just really appreciate both methods. So anyway, here we go. The absolute value of 2x plus 1 is equal to 7. So what I'm going to do is I am going to graph the absolute value of 2x plus 1. I'm going to show you what the graph of this looks like. We did something similar to this in the previous example. We'll graph this. We already know what it's going to look like, right? It's going to be a V shape, right? And then I will look at that graph and investigate the graph, find out when it is equal to 7. All right, folks, I graphed this line, 2x plus 1. Remember that it is a line whose slope is 2, whose y-intercept is 1. So here's the y-intercept. I went up 2 units to the right by 1, up 2 units to the right by 1, up 2 units to the right by 1, and so forth. And the line continued down here below the x-axis, but for this portion that was below the x-axis, I reflected it above the x-axis like we did in the previous example because we have to graph the absolute value of 2x plus 1. Okay, let me label some points for us. All right, I labeled some points. Now notice I only graphed this portion here, right? The absolute value of 2x plus 1. And I'm calling that y, right? So let me label my graph y. Where should I put that? Maybe over here, just a big y, all right? This is the graph of the absolute value of 2x plus 1. We have to decide, or we have to determine rather, when the graph of 2x, the absolute value of 2x plus 1 is equal to 7, okay? So I'm going to call it y sub 2. I actually called this one y sub 1 just to differentiate. So this is y sub 1 here. I could change this subscript here. So this is the graph of y sub 1, which is the absolute value of 2x plus 1, right? And then I'm going to call y sub 2 7. So remember, 7 is just a constant. So, and also remember that the graph of any constant is just a horizontal line. So this is the graph of y equal to 7. Or y sub 2 or whatever equal to 7, okay? So this is what this is the graphical approach. When does the absolute value of 2x plus 1 equal 7? Well, right here and right here. I'll highlight it. At this point, the absolute value of 2x plus 1 is intersects with 7. And so the question is, watch this, remember, solve for x, right? Solve for x. So give me the x values at the points of intersection. Give me the x values at the point of intersection. 3, -4. Those are the solutions to this absolute value equation. In other words, if you let x be 3, or if you let x be -4, then the absolute value of 2 times x plus 1 will be equal to 7. This is the graphical approach to find the solutions for this absolute value equation. We graphed this absolute value expression, which is a v. We graphed this constant, which is a horizontal line. Find their points of intersection. Now let's show the analytical approach. Now please remember the definition of the absolute value of a number. The absolute value of a number is this distance from 0. So for the absolute value of 2x plus 1 to equal 7, that means 2x plus 1 has to be 7 units from 0 on the number line. So this can only happen if 2x plus 1 is exactly equal to 7, or it's equal to the opposite of 7. So in other words, this is going to turn into a compound equation. I'll show you a quick little picture to try to convince you that you have to turn this into a compound equation. In order for this expression to be 7 units away from 0, it would have to be exactly equal to 7, right? Or the opposite of 7, right? So this shows that the expression has to be either equal to 7 or equal to -7. Now we just need to solve each one of these separately. So subtract 1 from both sides, divide both sides by 2. Over here, subtract 1, divide by 2. Look at this, folks. You have your two solutions, 3 and -4. These are the two x values that satisfy this absolute value equation. Now listen, we found those two same x values up here, but using a graphical approach, right? Look at these x values, 3 and -4. So this is the graphical approach, and down here I showed you the analytical approach, which I did kind of warn you that it would be a shorter approach, and some people may like this better because it's shorter, and I understand. It's shorter, it's very effective, but at the same time, this approach up here, the graphical approach, although it took us a while, I hope you appreciate it so that you can actually see a picture of what's going on, right? This graph is, the graph of this absolute value expression is a V. This is a horizontal line. So it's finding the x values at the points of intersection. Okay, guys, look at this next example. It says solve the following inequalities. The absolute value of 2x plus 1, we just graphed that. When is it greater than 7? The absolute value of 2x plus 1, when is it less than 7? So my tip here, my strategy is please don't do more work than you have to. My strategy or my tip here is use the graph that you just created. All right, let's look at the first one, right? When is the absolute value of 2x plus 1 greater than 7? So let's scroll back up to our picture. Come with me, and we're going to use the graph. Here is the graph, okay? Let me get rid of some stuff we don't need here. There. So look at this graph. What you see in blue, right, is the graph of the absolute value of 2x plus 1, right? You and I just walked through it a little while ago. The question we're trying to answer at the moment is when is this V shape basically, when is the graph of the absolute value of 2x plus 1, when is it greater than 7? Greater than 7. Greater than 7. Well, if you allow me to kind of butcher my picture, it's greater or larger than 7 on that interval and that interval, correct? So these two pieces show your solution. The absolute value of 2x plus 1 will be greater than 7 on this piece and then this piece. Now, let's be very clear. They're asking you to solve for x. So what are your x values? Well, it starts right here at, it's hard to see because I butchered it, but that's a 3 right there. So from 3 and then forever to the right, and then from -4, right, that's the x value, from -4 forever to the left. So the absolute value of 2x plus 1 will be greater than 7 from -infinity to -4, union from 3 to +infinity. Now be careful here. You do not put brackets on -4 or on 3. The only reason is because this is strict. So you are not including -4. You're not including 3. That's what the parentheses mean. If you would have put brackets on -4 and 3, you would be including those endpoints. You can only do that when this inequality is non-strict. So if this had been a greater than or equal to, then I would put a bracket on -4 and 3. All right, let's go back to the picture and try to figure out this solution. When is the absolute value of 2x plus 1 less than 7? All right, here's our picture. Now we want the piece of this graph that is less than 7. Well, it's less than 7, or below 7, if you will, from here to there, right? I highlighted it right now. From there to there. That portion of the graph is below 7. So what's going to be your answer? Well, the absolute value of 2x plus 1 will be less than 7 from -4 to 3. So in between -4, in between the x values -4 and 3, the graph is below 7. So that's going to be our answer. Now remember, you're going to want to use parentheses again on these endpoints. And again, it's because this is strict. Had that been non-strict, like less than or equal to, then you would put brackets on the endpoints, which means that you would be including them. So the great thing about the graph, now this is the beauty. I know it took a while to get the graph here, guys. I'm sorry, I'm scrolling a lot. I know it took a while to get this graph, but now that we have it, we're able to answer absolute value inequalities or questions about the graph fairly easily because we can just reference the picture, right? Now, there's an analytical approach for solving these absolute value inequalities, right? Right now, we just use the picture, we use the graph, so we use a graphical approach. There's an analytical approach for solving absolute value inequalities. It would take us longer to do the analytical approach than to just reference the graph, right? So there's pros and cons for both. I'm a big fan of the graphical approach, and I think you could probably tell. In this particular case, it was faster to use the graph since I already had it created than to go the analytical approach. But I will be showing you the analytical approach for solving absolute value inequalities, okay? All right, example 6, and we're winding down. We're almost done here. Let us solve this absolute value equation and then these absolute value inequalities. Now, this example will show you an analytical approach, but keep in mind that we do know how to show a graphical approach, right? We know how to do this. This graph here, the absolute value of 4 minus 3x, the graph will be a V shape, right? And we can start by graphing the line whose slope is -3 with y-intercept 4, but the portion of that line that is below the x-axis will just reflect it across the x-axis, which will give us the V shape. And then we'll find the x values at which that V intersects with the horizontal line y equal to 2, right? And then that will give us the two solutions here. Once we have that graph, we can answer these two relatively easily. So we did that already, though, in example 4 and 5. Now let's show an analytical approach for solving these inequalities in equation. For part A, what I'm going to want to do is take my expression inside the inequality symbol, absolute value symbols, set it equal to 2, and then I also want to set it equal to -2, because the absolute value of a number or an expression is defined to be the distance from 0. And the only way that the absolute value of this expression, 4 minus 3x, is equal to 2 units. In other words, the only way the distance of this expression from 0 is 2 units is if this expression is exactly 2 units away, or it's the opposite of that, -2, right? So what I'm going to do is, here, let me, to convince you, let me show you a number line. If this is 0, and if this is 2, and -2, the only way that the absolute value of this expression is exactly 2 units, that is to say, the only way that the distance that this expression is from 0 is exactly 2 units is if it is equal to 2 or if it's equal to -2, right? So this quick little sketch shows you absolute value equal to 2, right? 2 units away from the origin or 2 units away from the origin, or 0. So that's why I'm setting it equal to 2 and -2. So all we really need to do here is solve each of these equations. Now notice that we have a compound equation here, compound, right? 2 equations to solve. So let's solve the compound equation, subtract 4 from both sides, divide both sides by -3. So one solution is 2/3, right? And over here, subtracting 4, dividing by -3. The other solution is 2. So in set notation, you have 2/3, comma, 2. These are the solutions for the absolute value equation. Now, let's solve these inequalities here using an analytical approach. Let's start with this one, greater than or equal to. So in order to solve an absolute value inequality with greater than or equal to, you're going to want to split it into a compound inequality with the word or in the middle. Now this is very important. Compound inequality with the word or in the middle. This is for whenever you have an absolute value inequality with greater than or equal to. Now you just solve this inequality, subtract 4 from both sides, divide both sides by -3. Now you have to switch the inequality symbol, right, whenever you divide by a negative. So I have x is less than or equal to 2/3. And then over here, subtract -4 and then divide by -3. And you get x is greater than or equal to 2. So in interval notation, our solution will be -infinity all the way to 2/3, bracket, union, bracket at 2, and then positive infinity. This says include all of the numbers that are greater than or equal to 2. That's what this interval is. This says include any number that is less than or equal to 2/3, and that's what this interval is. Notice I have brackets on my endpoints, and that is because this inequality is non-strict, which means you are to include your endpoints. Your real numbered endpoints, right? Negative infinity and positive infinity are not real numbers. So put brackets on your real numbered endpoints. All right, let's solve the last one. So we already did these two, right, everybody? So let's solve part C. This inequality is less than or equal to. So the way I'll solve this is by taking my expression and saying that it has to be less than or equal to 2 or greater than or equal to -2. This is called a double inequality here because you have two statements within one. Two statements in one, all right, or two inequalities. Now, what the idea here is you want to isolate the variable right in the middle. So in order to do that, I'm going to subtract 4 from all three parts. Make sure you subtract 4 from all three parts. You get -6 is less than or equal to -3x is less than or equal to -2. Next, you're going to want to divide all three parts by -3. Now be careful. When you divide by a negative, all your inequality symbols must switch. So you got +2 greater than or equal to x greater than or equal to 2/3. Let me scroll down a little bit here. So writing this from least to greatest here would be equivalent to 2/3 less than or equal to x, which is less than or equal to 2. Make sure you turn that around, okay, everybody? Don't leave it like this. Write it from least to greatest, right? Because we read from left to right. So this is your final solution set. In interval notation, it is a bracket at 2/3, comma, 2. Right? So it's all the numbers that are between 2/3 and 2. So this example showed you an analytical approach for solving absolute value equations and absolute value inequalities. In this example, it's going to be short, but they're important. These are special cases. I'm going to give you 3 different special cases. Here's the first one. The absolute value of 3x plus 5 is equal to -5. Now listen, this left-hand side is always positive because the absolute value of any expression is always positive by definition. So really this is asking you, when is something positive equal to something negative? Impossible. Because this is impossible, your final answer is no solution. The solution set is empty, right? So in interval notation, you would say no solution. Something positive is not equal to something negative, ever. No solution. Don't use this symbol for 0. It means no solution. Let's look at another special case. Here we have another special case. The absolute value of 3x plus 5 is less than -5. Using my same logic, when will something positive be less than something negative? Never. Something positive is never less than something negative, right? It's actually the other way around. So this one, again, is no solution. For this last special case, when will something positive be greater than something negative? Always. Something positive is always going to be greater than something that's negative. So this relationship right here will always be true. No matter what you plug in for x, the absolute value of this expression will always be greater than negative 5 because something positive is always greater than a negative. So here, be careful, the answer is not no solution. The answer is all real numbers. And of course, all real numbers in interval notation is negative infinity to positive infinity. Okay, so be careful about these special cases. We're going to wrap up this lesson with this example. This is an absolute value equation that has two sets of absolute values. Now, think about it. When will the absolute value of this expression be equivalent, or have the same value, as the absolute value of this expression? The absolute value of this expression will be exactly equal to the absolute value of this expression if, or when, these two expressions that are within the absolute values are equivalent or they're opposite each other. Let me give you some examples. The absolute value of 7 is equal to the absolute value of 7, of course, because 7 is equal to 7, right? The expressions are equal. The expressions within the absolute values are equal. But the absolute value of 7 is also equal to the absolute value of negative 7, isn't it? And this is true because the expressions within the absolute values are opposites, right? And I can give you many examples. The absolute value of 5 is equal to the absolute value of 5. The absolute value of 5 is equal to the absolute value of negative 5. These statements are true because the expressions within the absolute values are the same or they're opposites. So that's the logic I'm going to use here in this for this example. I'm going to say that this statement will be true if, now watch this, x plus 6 is equivalent to 2x minus 3, or x plus 6, watch this, is equal to the opposite of 2x minus 3. Now, you did not have to take the opposite of the second expression. You could have taken the opposite of the first expression. In other words, you could have said the opposite of x plus 6 is equal to 2x minus 3, okay? All right, so all you got to do now is solve each of these equations. But please notice it turned into a compound equation. Go ahead and solve each one of these separately, and let's see if both you and I agree. So you can go ahead and pause the video here, pause it, and solve each of these equations for x. Okay, I hope you and I agree that the solutions are -1 and +9. I wrote these solutions in set notation. You should do the same, okay? All right, so I hope you learned. I'm sure some of it was review, but I hope you also learned especially the area of showing a graphical approach for solving an absolute value equation and for solving absolute value inequalities. So catch you later. Good work.